you're driving in your car, you're hitting the gas, you are actually accelerating toward the left here, and that's causing the ball that's hanging from a string from your ceiling to kind of go backwards. So the first step of this problem, oh, by the way, we're trying to figure out what angle the string makes. We've assigned this angle the variable theta. So we're going to make a free body diagram here. Well, before we do that, I just want to kind of indicate that the acceleration is given as 1.2 meters per second squared. That's what the car is accelerating toward the left. So we know that that's what the ball is also accelerating at. So here's our free body diagram. We're just going to write vectors to represent all the forces on the ball. That's what a free body diagram is. So there's always a gravitational force if something's on a planet or even a moon. And we could write that as F subscript g, the force due to gravity, or we could write it as in the slide, the mass of that object times the acceleration of gravity. Because due to Newton's law, Newton's law says that a force that accelerates an object must be equal to that acceleration times the mass of the object. So this is the mass times acceleration. The acceleration that the ball would be experiencing vertically if there weren't another force pulling in the opposite direction. That force is the tension force in the string here. So we'll call it Ft for tension, force of tension. And we can separate the acceleration into horizontal and vertical components. Actually, it's entirely a horizontal acceleration. Your car is driving to the left horizontally, and that's the direction of the acceleration. We can assume it's on flat ground, so the car and the ball aren't raising or lowering at all. So if there is no acceleration vertically, that means there is no net force vertically. And what that means is that since there's a gravitational force acting downward on the ball, the vertical component of the tension must exactly counteract the gravitational force. So this vertical component of the Ft, the force of tension vector, must be equal in magnitude to the force of gravity vector, but in the opposite direction. So we'll go ahead and call that vertical component of Ft mg, but upwards. And if we continue to decompose the Ft vector and give its horizontal component here, this would be the force responsible for accelerating the ball. And I guess we can call that force of tension in the x direction. And since this is the only horizontal force to act on our ball, this must be the force responsible for accelerating it at 1.2 meters per second squared. So we can say that this x component of the tension force is the mass times the acceleration because of Newton's law, F equals ma. Okay, let's review real quick and just go over again what we did, maybe in different words. So we decided that we had a force of tension, and we decided to decompose that vector into its x and y components. So instead of looking at a tension going diagonally, we're looking at two tensions, one going horizontally and one going vertically. So we can either look at that overall tension going diagonally, or we can look at the two vertical and horizontal components of it, and we're looking at those two components. And the other thing we decided was that the vertical component of the tension here must exactly counteract, must be equal in magnitude but opposite in direction to the gravitational force pulling downward on the ball. Because even though this ball is accelerating horizontally, it's not accelerating vertically, up or down. Okay, moving on. Let's make a triangle. Here's a good triangle to make. We know that this side here is the vector with the magnitude mg. So there's that side. And we know that the hypotenuse here is that tension force, and we know that the top side is the force responsible for the horizontal acceleration, which we decided was ma. And if we look at our diagram over on the left here, we can see that the angle theta is the same as this angle here in our triangle. So now that we've figured out all this stuff, we've found our triangle, we need to figure out, there must be something we can do to figure out what theta is. And when I look at this triangle, I see that we know the ratio of this side length to this side length, because m is constant, and we know that a is 1.2, and we know that g is 9.8, the acceleration of gravity. And these sides are the smaller sides. ma is the side opposite to the angle theta, and mg is the side adjacent to the angle theta. So here's a case, soka toa, where we use tangent, toa. Toa means tangent is opposite over adjacent. So what we can conclude here is that tangent theta equals the opposite side length ma over the adjacent side length mg. And when we put in the values we know for a and g, we get 1.2 m, because a is 1.2, over 9.8 m. And the m's cancel out. And 1.2 over 9.8 is 0.122. So we get tangent theta equals 0.122. We want to find the angle here, so here's a situation where we use inverse tangent. So this is, the inverse means the little to the power of -1, if you're looking for that key on your calculator. So what theta actually is the inverse tangent of 0.122, and that's just about 7 degrees. And that is part A. Part B, what about when the car moves at a constant velocity of 90 kilometers an hour? That's pretty fast. But constant velocity, that means there's no acceleration. No acceleration vertically or horizontally. That means that there can be no net force horizontally if there's no acceleration. And if this ball is hanging from any angle other than 0 degrees, there's going to be a horizontal component to the tension. So it has to be 0 degree angle. It's just hanging straight down, so that the tension in the string pulls exactly straight up, neither left nor right.